Hi, and welcome back to Hardware Design. Um, 2 weeks ago, we were working on this quadratic equation unit. We've been calling it QuadRoot.vp. You can see what it does is it finds this opposite of b plus or minus square root b squared minus 4ac over 2a thing. The way that we built it is we assume that a is always 1, so there's only a b and a c, and then we need to calculate if r0, what r0 is, and if it's valid, and what r1 is, and if it is valid as well. In general, what we're going to do is we're going to calculate that two different ways. So we're going to use the difference that goes in the square root, so this b squared minus 4ac, to determine the number of roots, because if it's positive, as in this case, then r1 is valid. And then if it is positive or 0, it is one root. So this is positive and non-zero, and this is positive and 0, right? So if you have 0, there'll only be one root. If it's positive, you have 2 roots, and then if it's imaginary, it's 0, and so we don't really care what the output is. It might be useful in other designs to know what the roots are, but not for the design we're caring about. All right. So our notes from last time were that we need to write a test bench and verify. So what we're going to do is we're going to generate B and C with random. This probably needs to be elegant. Not elegant, but needs to be a little clever. So one of the things that I'm worried about is that we might accidentally generate things that are kind of not too interesting to look at. So we may want to create a few different set of test patterns to play with. But otherwise, the checks are pretty easy. Is that this should be exactly equal to 0, though this is probably needs to be an error bound, and then this probably needs to be an error bound as well. It's because I think we've done some rounding. We may not have the exact right answer, but we'll hit that road when we get to it. Alrighty. So do I happen to have the other version in there? Yeah. So just opened another view into the Emacs section. Yeah, so I haven't done anything. So let's take a peek at another top file to get us going. So we'll look at verif top sort 6. No, I don't like this one. So in general, you write one or two good test benches, and then you keep using them. So we'll do this. So we'll look at the microcode test bench, because I'm pretty sure this has a lot of the stuff that we need. So yeah, so we like that stuff. They don't need the tape. So we wrote module, so we better write end module or bad things happen. We have some signals here. We'll do that one. I think the framework I'm using uses these signals, so we'll do that. There we go. Reset task. Yeah, I don't know that I like too much of this. It's probably enough for now. So let's fix some things up. So need to copy over the parameters. So we have, we call this QuadRoot. This would be my under QuadRoot. So the bit width is that. Call this integer width. We'll call this fraction width. So bit width is that. This is IW, so this is integer width. This is fraction width. Alrighty. And so then we're just going to steal these signals from here. There we go. Logic signed, logic signed, logic signed. Commas become semicolons. Don't forget the last one. So those are those folks. Let's see what other things I can borrow. Oh, there's a generic bench that's good to have. Then, yeah, let's have a simulation narrative. So let's see. So what I'm thinking about right now is what I want to do with the narrative. So I think we want to write two vectors. So one is going to be random stimulus. So we'll do 3. Random but small stimulus. And counted loops stimulus. Okay. So let's do this one first because this sounds hard. So the idea behind counted loops is we'll start at some small number, let's say minus 256 to 256 times, on both sides. So we'll increment B and C through those values, and it should theoretically just work. Okay. counted vector and task. So what we will do is, for I equals minus 255, myself into I, j, I less than 256, I plus plus, begin, end, for j equals minus 256, j less than 256, j plus plus, begin, end. We can say, at neg edge clock. So now we have a delay in, and then we could say that b is equal to I and c is equal to I. So how will we add this into our narrative? So what we'll do is we'll just call counted vector that many times. Then we'll just collect all the activity from that. Counted vector. We're going to make this neg edge clock. There we go. So now we have the perf there. And just some cycles to count out. And then, well, it's right. Starting test. Dollar time. Okay, that works. So what else do we want to steal from the multiplier? So we just built our driver. So we'll do this. Let's see our notes. Okay. So we're going to do a little bit of lazy verification. So we're going to assume that we're dealing with somebody who's on the up and up, and that if something is valid, if they think something is valid, they're going to pass valid. So one hole in our plan is if there is how do we make sure the root count is right? So that's a problem. But for now we could certainly write something like if R0 under valid, then we'll call it the R0 check, assert, now that R0 times R0 plus B times R0 plus C, and then I think, so if R0 and B and R0 all have the same fraction, then all we really need to do is shift C left by fraction. So that's what we're going to do. Should be so I think I want 0.01. Let's say 0.001. So let's say equals 0. And then we'll see whether or not that works. R1 check. Then, yeah, this is going to break in a not fun way, because I don't really think that this is. Well, did we round R1 or 0 or R1? So yeah, we ended up throwing away a bottom bit in this step. And yeah, we'll keep going forward, but we'll make a note. Note that this probably needs to be bounded rather than exactly 0. And then, let's build a monitor for us. So Alan just tuned in. So I think 2 weeks ago we started building a unit to calculate the roots from our quadratic equation. So I have a module that implements this minus b plus or minus for some fixed point numbers. Tells me which of the roots are valid. So R0 is always going to be valid before R1 is going to be valid. Calculates it out. And the idea, I'm going to use this unit for some graphics, stuff that I'm going to do later. It's going to help me calculate some integrals. Well, it's going to help me calculate the bounds of integrals. This test bench is to test the QuadRoot module. So right now I am writing assertions to check that these are the roots. So root 0 times itself, so x squared plus b times x plus c should be equal 0. So these should be arithmetic shifts instead of Boolean shifts. And right now we have a vector. Right now our stimulus is just counting from minus 256 to 256 across both. So hopefully it gives us something interesting. It's been a long time since I've thought too much about what the roots need to be to get surreal valued things, so it'll be interesting to see what happens. And we're at the... Yeah, so not non-complex. So I want the real roots, either the two real roots or the single real root. I don't care about the imaginary roots. So in the application I'm interested in, I have a line intersecting a curve, a quadratic curve. And the imaginary roots represent non-intersection. So the curve never intersects the line except for in the imaginary plane. So the real roots represent the real intersections. But you're right. If I were doing a fancier version of this, I would actually be interested in making sure that I'm producing complex numbers. If one of these days we do a fast Fourier unit or some signal processing units where we care about phase and magnitude, we'll calculate the complex values instead of the real values. But yeah, that's a good question. It's also easier if we're not dealing with it. But good questions. So right now I am writing a monitor to just print the output for me. So let's see, what's the easiest way to write this? So we'll say something like B. So we'll do dashes since I'm doing colons. So this would be C. And then we'll do R0, R0V, R1, and R1V. %6D, %B, %6D, %B. And help us debug this stuff. It might be helpful to calculate these numbers. So I'll actually just put this right here, and we'll call this the R00. R10 should be this. Because it'll be faster to just look at the output than guess what's going on. Move my cursor. Let's make sure that all these are 60 because I don't want to print huge numbers. So this should be 60. Cool. Oh, now I need to fill in the numbers. So this was B, C, R0, R0 under valid, R0 under 0, R1, R1 under valid, R1, 0. I think that's it. So I think that's the bare minimum we need to... Yeah, I must have done something horrible to Firefox. Yep, so now we make gen module name equals QuadRoot. GB requires explicit package name. So we forgot to actually generate our generic bench. So let's do that up here. My $GB equals generate generic verif under bench we'll call it TB. Hopefully that didn't need a specific name to work. Now I'm going to be I call it basic bench. So in the worst case, it is now the same name I use everywhere. So hopefully there's no issues. Failed to instantiate my QuadRoot. Error, syntax error at line 9 of QuadRoot.vp. QuadRoot.vp, line 9. We forgot a paren. We also forgot our good habits. That's worrisome. Okay. I guess this isn't too long. I would have thought there was more craziness. Okay. Yeah, I'm not seeing anything too crazy. So we'll just call compile. See what evils I've wrought. All right. I think those are supposed to be semicolons instead of commas. That's not even the right module. There we go. So some of the errors it looks like is I forgot to declare some of the signals. So this is our 0 under 0. Looks like I forgot perf. For some reason I have something called AB count. So for the folks doing homework, I probably stole this from a module that's counting AB valids. There's the 63 is logic. I really want to use commas today. We're getting there. All right. So apparently I just am spelling 0 weird today as well. Let's just double check. Yeah, I spelled that right there. Seemed to want to use a 0 as the O in 0. All right. Error, cannot find cell in LibreList. Ooh. Config rule. Ooh. Ooh. So this means that I am not importing the right Verilog file to do this. Yikes. Wow. Okay. So this is kind of a showstopper. So the issue is I've used this module dw_root, and it requires that I import a certain library into the compiler for running. And it's going to take me probably a good 30-40 minutes to run down what exactly the file is. And I don't think you guys care at all. I imagine that the reason it's not working is that I may have removed it for the class. So this is the flow I use for the class. I may have removed the ability to use these modules specifically for the class, so that folks wouldn't do the assignment by just instantiating the equivalent designware module. Because more or less one of the ways that I come up with homework assignments is looking at the designware library and going, that seems like a fun thing to build. So I'm going to call it a night. Sorry for the short video. Next time, so let's see. So next time I will show the fix for adding designware modules to the makefile. I'm probably not going to propagate the change to the class directory. I'm probably going to keep it local, and maybe next year's handout directories will have it. And then we need to finish verification. One of the things we need to do is check our 0 comparison, and then we need to add a test to see if root counts are wrong. And C, just kind of run it, and then we'll pick up with some synthesis and see, how expensive is a square root module. Great. You probably noticed that I do this every time, so some of this is to let you guys know what I'm going to do for next time, but this is also a good habit for programming. So I have a lot of things bouncing in my head, and this is one way that I know what I need to do the next time I sit down. The other thing is that it's actually, psychologically, it works really well to know exactly what you're doing as soon as you sit down, so you kind of get into the flow much faster. So if you aren't doing this and you program in fits and starts, sort of like this vlog, this is not a bad idea. Is keeping a little to-do list of how to get into the next task. It's also a good idea to do this at night before you go to sleep, so the next day you have some easy stuff to do when you get going. All right, we'll call this short. Sorry, guys. Have a wonderful night, and I'll see some of you Friday, but most of you I assume I'll see next Wednesday. Have a good one.